Recall when we were examining the motion of an object in 2 dimensions, we introduced a Cartesian coordinate and a position vector. Now, let's suppose the object has moved to a new point along the orbit. Well, we'll write another vector, r of t, and let's say this took a time delta t to the new point. And what we want to define is the displacement of that object. So that's a vector delta r. And recall that a vector at time at t plus delta t is equal to the old vector r of t plus this displacement vector delta r. Now, what we want to consider is a limit as delta t goes to 0. And let's just look graphically at what that means. As we move this delta t, as delta t gets smaller and smaller, and our object is getting closer and closer to its position at time t, and the position vector r at t plus delta t is getting closer and closer to r of t delta t, the key fact is that if we drew a tangent to the orbit, then the limit of delta r is approaching tangent to the curve. So in the limit delta r, the direction is tangent to the orbit. So that's our first key property of delta r. Now, the second thing we wanted to express is if we write delta r as a displacement in the I hat direction and a displacement in the j hat direction. Now again, maybe we can just clean this up a little bit and see what we mean by that. So here's our delta r. And we have a little delta x in this direction, delta y in that direction. Remember, delta x or delta y can be positive or negative. That's all right. Now, if we want to define our velocity as the limit as delta t goes to 0 of delta r over delta t, then what we see is we have two pieces, the limit as delta t goes to 0 of delta x over delta t I hat, plus the limit as delta t goes to 0 of delta y, delta t, j hat. And the definition of these limits, we'll write that as the derivative dr dt. So the velocity is dr dt, and that's equal to dx dt, how that coordinate function is changing in time, I hat, plus dy dt j hat. Now, as far as notation goes, we write this velocity as an x component of the velocity plus a y component of the velocity, where the x component vx is dx dt, and the y component is dy dt. Now, recall that the direction was tangent to the curve, but the magnitude of the velocity, what we call the speed, is just the sum of the squares of the components, the square root. And so now we've described what we refer to as the instantaneous velocity. So far we've looked at a trajectory in 2 dimensions. Let's again consider some type of motion where we choose a positive y-axis, a positive x-axis, an origin, unit vectors, I hat and j hat, and we'll have some type of trajectory where our object is moving like that. We know that at this particular time, the velocity is tangent to this trajectory at that point. And now what we'd like to do is try to describe, we've described its 2 components, vx and vy, as a vector. So if we did vector decomposition, we would write a vector like this and a vector like that. This is the x component. That's the y component. And now if I define this angle theta, we know that a vector has a direction and a magnitude. We've seen that we call the magnitude the speed. So that's just the sum of these components squared square root. Speed is always positive, so we always take the positive square root. And now what about the direction of this vector in the xy plane? Well, we can see from our geometry that the tangent theta is given by the y component over the x component. Or one could say that the angle theta at this given time is the inverse function of Vy over Vx. And so now we've described not only the direction of the velocity, but the angle that it's making with the horizontal axis. And so we've now completely described the velocity, instantaneous velocity vector at time t in terms of its two component functions, its speed, and the angle that it makes with the positive x-axis. Let's consider a two-dimensional motion. Suppose we have something like a projectile motion, and we have an object moving. Let's now describe how we can describe this motion with vectors. So the first thing we always want to do, and let's remind ourselves of the steps, is we want to choose a coordinate system. Now, what does a coordinate system consist of? It consists of an origin. It consists of two axes. In this case, we'll identify the positive direction for each axis as plus x and plus y. And at every single point in space, so if we had any arbitrary point P, here, P, let's call this P1, we have a choice of unit vectors I hat 1 and j hat 1. Now, what makes Cartesian coordinates unique is that no matter what point we're at, the unit vectors are all the same. So we could erase all these indices for that particular point and just have an abstract set of unit vectors I hat and j hat. Now, normally what we'll do is we'll just put those off to the side. So in our Cartesian coordinates, we now want to define the position vector. And the position vector is a vector from the origin to where the object is. So we'll write that position vector. We'll denote it by r of t, because as this object moves along its trajectory, that position vector is changing. And we'll write down r of t in terms of two coordinate functions, x of t and y of t. And so our vector, position vector of the object, r of t, is equal to x of t I hat plus y of t j hat. And one of our main goals is to figure out what these position functions are for the motion of objects. So this is how we describe an object in a Cartesian coordinate system undergoing two-dimensional motion. What we want to analyze next is what is the velocity of that object. Let's now consider two-dimensional motion, and let's try to analyze how to describe the change in velocity. So again, let's choose a coordinate system. We have an origin, plus y, plus x. And let's draw the trajectory of our object. And now let's draw the object at two different times. So for instance, if I call this the location at time t1, and a little bit later here, this is the location of the object at time t2. We'll call our unit vectors I hat and j hat. Now, we know that the direction of the velocity is tangent to this curve. So if we draw v at time t1, and over here, notice the direction has changed v at time t2. And what we'd like to do now is describe, just as before, that our acceleration a of t is the derivative of the velocity as a function of time. What that means is the limit as delta t goes to 0 of delta v over delta t. Now, it's much harder to visualize the delta v in this drawing. And partly the reason for that is these velocity vectors are located at two different points. And right now, the backs of these vectors have different places in space. But remember that delta v is just v, in this case, at time t2, minus v at time t1. And our principle for subtracting two vectors at different locations in space is to draw the vectors where we put the tails at the same location. So here's a tail at this vector. We're just going to translate that vector in space. That is still v at time t1. These vectors are equal. They have the same length, and they have the same direction. And so delta v is just the vector that connects here to there. That's what we mean by delta v. And so you can see in this particular case that it's not obvious from looking at the orbit what the delta v is. So what we need to do is just trust our calculus. And so when we write the velocity as dx dt I hat plus dy dt j hat, and we're now treating each direction independently, we call this vx I hat plus vy j hat. So that's our velocity vector. Then our acceleration is just the derivative of the velocity. We take each direction separately, so we have dvx dt I hat plus dvy dt j hat. Now, again, notice that velocity v of x is already the first derivative of the position of the x component function. So what we really have here is the second derivative of the position function in the I hat direction, and the second derivative of the component function in the y direction. And that is what we call the instantaneous acceleration. Now, again, this is sometimes awkward to draw, but you always must remember that this x component of the acceleration, by definition, is the second derivative of the component function or the first derivative of the component function for the velocity. And likewise, the y component of the acceleration, ay, is the second derivative of the component function for position. And that's also equal, by definition, to the first derivative of the component of the velocity vector. And that's how we describe the acceleration. As before, we can talk about the magnitude of a vector. And the magnitude of a, we'll just write as a. It's the components squared, added together, taken square root. And that's our magnitude. And so now we've described all of our kinematic quantities in two dimensions: the position, the velocity as the derivative of the position, and the acceleration as the derivative of the velocity, where each direction is treated independently. One of the most common motions we see in our everyday lives is the path of an object moving, thrown, and moving through space. Now, this type of motion has a very famous name called projectile motion. And when we look at it, let's introduce a coordinate system, I hat and j hat. Here's our plus y-axis and our plus x-axis. Then, in order to understand the kinematics of this motion, we'd like to apply Newton's second law. So separately, we'll draw our object. It has gravitational force acting downward. Remember, our unit vector is in the j hat direction. And so when we write our equations of motion, F equals ma, we have two different directions. In the j hat direction, we have the gravitational force downward, minus mg. And remember here that g is our positive quantity, 9.8 meters per second. And we have may. Newton's second law equates these two different things. And we'll write it like that. So those two quantities are equal. And so our conclusion is that the acceleration is equal to minus g in the y direction. Now, likewise, keep in mind that we have our horizontal direction as well. And notice there, we're now assuming that there's no horizontal forces. In the real world, there can be all types of air resistances. But here, for the simplicity of this model, we have no horizontal forces. So we have 0 equals max. And so we have our separate equation, ax equals 0. Now, both of these equations are equations that we've already been working with in kinematics. Here, we have a constant acceleration. And here, we have 0 acceleration. So using the results that we had earlier from integration, we can write down the equations of motion in the y and the x directions. First, we'll write the velocity. Vy as a function of time is equal to some initial value. And because the acceleration is negative, minus gt. You can test your integration technique to see that. And the position as a function of time, remember, is just some constant value. This is our constant y naught. And we have plus vy naught t minus 1/2 g t squared, again, doing integration. Now, the horizontal equation of motion, the x of t, because there's no acceleration in the horizontal direction, this is a constant value given by the initial value of the component of the velocity in the x direction. And the position, x of t, is then equal to some initial position plus vx naught t. And so those are our functions of time for the components of the velocity and the components of position. Now, for our particular example, it's much easier. Here we have x naught equal to 0. Notice that our object is starting at the origin. And so that tells us that x as a function of time is just vx naught t. I'm dropping the parentheses t. Remember, that's not a product. It's just a function of time. And given this fact, that tells us that t is x divided by vx naught. And now I can take this value of t and put it into our vertical equation. And I get vy is some initial value plus vy naught x over vx naught, substituting for t, minus 1/2 g x squared over vx naught squared. When we described projectile motion, we had an equation describing y as a function of t, an equation describing x as a function of t, the horizontal motion, the vertical motion. And here we have a separate equation which is describing the y as a function of x. Notice there is no time involved in this equation. Now let's try to look at graphically what we're seeing here. So for instance, when we look at a plot of the motion of y versus x, we can see the vertical component going up and down, and we can see the horizontal component moving to the right, while the object is following this trajectory. And this is a parabolic trajectory of y as a function of x. Now, if we wanted to actually plot out y as a function of t, then here we can look at the simulation where we're just looking at the y component, and you can see that that motion too is a parabola. However, what's crucial to look at is that it's y as a function of t and not y as a function of x. Finally, we can look at the horizontal motion, and again recall that when we looked at the trajectory as y as a function of x, you can see the horizontal motion component. Let's plot that separately, x as a function of t. And when we make that plot, you can see that this is just a linear equation in time where there's some initial condition, x naught. And so that's the plot of x as a function of t. And so we see three separate representations of this motion: y as a function of x, y as a function of t, and x as a function of t.